So we had been looking at reducing the storage required for an image by reducing the number of pixels in the image. If you throw away some pixels, you can try and fake putting them back in afterwards using interpolation. And then we went on to consider how, in addition to reducing the number of pixels, you can reduce the amount of data required to store each pixel. And when we're using RGB color, 24-bit color, we need 24 bits for each pixel. And the actual bits tell you what the color is. But we started looking at this idea of indexed color, where you have a limit on the number of colors in the image. So each pixel is one of 256 different colors, or each pixel is one of 128 different colors. You have a set number of colors. And then depending on the number of colors you have, well, you will need a certain number of bits then to represent the color. So as we'll see later, GIF, for example, has a maximum of 256 colors. So in a worst case scenario, you're talking about 8 bits per pixel instead of 24 bits per pixel. But obviously, if you're going from 16 million colors to 256 colors, well, something's got to give. And what we're going to start looking at now is, well, what gives? So supposing this was a 24-bit image, we saw this the last day, we might decide that this is going to be a 2-bit image, and so each pixel then is just one of 4 colors. So if you were actually looking at the raw data for this, the top left pixel here, this would probably say 0, 0, next pixel would be 0, 0, 0, 0, 0, 0, and so on until we get like 0, 1, that would tell us that's the next color. So just as if you only had 4 letters in an alphabet, you would only need 2 bits to represent each letter. Just as if you only had 4 students in a class, not unlike today, you would only need 2 bits to represent each student. And if you've only got 4 colors, you only need 2 bits to represent each pixel. There is an overhead though associated with that. Knowing that a pixel is color number 1, or a pixel is color number 17, or a pixel is color number 54, doesn't tell you what the actual RGB value is. Like in 24-bit color, the sequence of bits to represent the pixel also tells you the color. It's everything you need to know. In indexed color, you need an index or a color lookup table. And what that does is it maps each of the pixel values, each of the numbers of the colors, to the RGB values. So it's a bit like painting by numbers, where you have pot number 1 has a particular color paint, pot number 2 has a different color, pot number 3 has a different color, pot number 4 has a different color. And on the canvas, you just have 1 and 3 and 1 and 2. You don't specify the color, you just specify the index into the color. And this is like that. So the first set of pixels there at the top left, they're color number 1. A program displaying this image or decoding the image would need also to know what the actual RGB values of color number 1 are. Okay? So each pixel's color then is stored as an index into the color lookup table. It's a bit like painting by numbers. So when we're talking about indexed color, this is what we're talking about. So when you have a grayscale image, the sequence of bits gives you a number. That number tells you how bright the pixel is. When you have an RGB image, the first 8 bits will tell you the red value, the next 8 bits will tell you the green value, the next 8 bits will tell you the blue value of that pixel. In indexed color, all you're told is color number 74. You have to go look up what color number 74 is, and that's in the index. That color lookup table is also known as a palette. And it turns out that you can say to Photoshop, okay, for this image here, which has lots of colors in it, I want to reduce the number of colors down to 256. Can you pick the best 256 for me? Because you see what happens is each color is forced, each pixel is forced to the nearest color that's in the palette. So if you had lots of blues and greens in your image and your palette had mostly oranges and reds, they mightn't get used. That could be quite wasteful. So usually what we do is we take the image, we analyze it, and then we say, okay, for that image, here's the best 256 colors. You can imagine if you're manufacturing paint by numbers kits. If you have do a fabulous painting of the Nevada desert and do a fabulous painting of West Cork, you might end up using different, colors in your paint pots. I think I've flagged that metaphor now and I've got as much out of it as we can, so we'll just go on. So if you're going from 24-bit color, 16 million colors, down to 256, the trick is to pick the best 256. So Photoshop here has chosen these 256 colors as the best value for money when it comes to coding this image. So for example, there may be a pixel there. Like if the image only has 256 colors in it, then sure, you're laughing. Every pixel gets represented in the color lookup table. But there may be a pixel in here that's a color that's not in the palette. But if you choose the palette well, the impact will be minimized. So this palette goes with this image. When asked to choose the best palette for this image, obviously we've lots of blues and some greens and browns and greys. This image here, if you had a palette that had lots of blues in that and lots of greens, will you be wasting slots in your palette? Now there are also fixed palettes. There are occasions when you want to, there are advantages to using a set palette, a predefined palette, one that's not adapted to the image. So you can have a general purpose palette, and you may need to use that. For example, when I first started working, it was typical to have a display that only did 256 colors. Now you could pick any 256 colors you wanted, but if you were showing a bunch of images on the screen at the same time, they would all have to have been rendered with the same palette. And if they didn't have the same palette, you'd have a palette clash. With the web, it came to pass that if you were looking at a 24-bit image on a constrained display within a browser, there was only a subset of colors that worked across every browser. And so we used to call that a web-safe palette. And you would go for that palette because then the color wouldn't be changing twice. But those constraints are largely irrelevant nowadays. So nowadays, typically, you adapt the palette to the image that you've got. So looking at this image here, which palette do you think goes with this image? This is obviously a trivial one, just to get you warmed up. You'll notice here that not all of the slots are used in this palette. When we first looked at this image, I remember saying, I don't think there's even 256 colors in this. As it turned out, I was right. So every pixel color in this image got a slot in the lookup table. Now, in fairness, at most, this would only have had 256 colours anyway. So that it may do with slightly less than 256 is no great shock. But every shade of grey in this image was given its own slot in the colour lookup table. Now, as it turned out, there's no saving made there because a grayscale image would only have been 256 shades of grey anyway. But if it had been coded as an RGB image, it would have been very wasteful. Looking here, which palette do you think goes with that image? Should you wake up one morning with a headache, a hangover, and you see both the Statue of Liberty and the Eiffel Tower, you're probably in Las Vegas. But you could be in Paris. There's a Statue of Liberty in Paris as well. The French made a small one in memory of the one they sent to New York. I think we can rule out the bottom right one there. It's just a question then, which of these? It could be either. I think this, on balance, is a bit dark. I think there's more kind of saturated colours here. And let's face it, if it's Las Vegas, you're looking at saturated colours. Yep, that's right. Okay. How about this one here? I'd say we could rule out the top one. There isn't enough blue in the top one for it to have been chosen for this particular image. It could be the bottom one, but I think there's too many browns in there. I'm going to go for the middle one here. Lee, what do you want to go for? Top one, yeah. I think there are quite some highly saturated colours in this image, and there's some highly saturated colours in this palette. I think everything here is a bit too, well, this is just too blue anyway. There's no reds, you know. How about this one here, John? What do you think? We can rule out the green anyway.
Yeah.
That 40 shades of green is for somewhere in Kerry.
Top one, I imagine.
I think the top one, I would think. The bottom one there doesn't have enough variety of colour, and there's quite a lot of variety in that image. Yep. You, sir, what do you think?
The one on the right.
I would say the one on the right. Certainly the one on the bottom is no good to us anyway. There's no blue in this image. It could be the one on the top, except there's no orange really in that. No. So I'd say it's the one on the right. Yep, good job. Next up here, which of these images do you think goes with this palette? We can rule out the bottom right one anyway. You'd go for bottom left. I would think so, yeah. I mean, there's some brown in this too. Interestingly, they're all from the same city. I wonder, could you actually, if you had photographs from the same city on the same day, would they all end up with very similar palettes? Certainly, San Francisco has a palette. Cork has a palette. You know, Las Vegas has a palette. Some interesting, maybe an interesting research project there now for you. We're going to go with bottom left, I think, but I think top right could be an option also. Yep, well done, good job. What about here? You'll notice as well that this palette doesn't have 256 colours. You can specify how many colours you want. You can say I want 256 colours. You can say I want 250 colours as well. Generally though, we go 256, 128, 64, 32. Because if you have 32 different colours, you can do that in 5 bits, right? If you have 33 different colours, you're looking at 6 bits. So the difference between 31 and 32 is very small. The difference between 32 and 33 is quite big. So typically we use those powers of 2. I think we can rule out there the car in Havana. There's not a whole lot of green going on there. And the bottom right there, I don't think there's enough blue in that palette to do the sky well. And the middle one there is a bit monotone as well. So it would be the top left or top right. Interestingly, to support my theory, they're both from the same city on the same day as well. I would think there that this little bit of blue here, these bits of blue, puny and all as they are, might make me go for the one on the left rather than the one on the right. Yep. So you get the idea? So you generate the palette based on the image. And that means then that, okay, you've only got 256 colors, but at least they're well chosen 256. Ireland for a change, but not as green as we would have expected. If I told you I had a picture of Ireland, you might have gone for this. But having seen the picture now, top or bottom? I think bottom. Yeah. Cool. Okay, so that's palettes. No. So far, so good. But the next thing we're going to consider is dithering, okay? So we're in the same territory here now. We have an image that's 250, 16 million colors, whatever. We're reducing it down to an indexed palette with a certain number of colors. And as we reduce the number of colors, obviously the quality of the image gets reduced. You start to see it first in areas where there's subtle gradients of color. You start to see the banding. So just we had that gradient from green to yellow. You get these stripes. Similarly, you see this banding here in the sky because, here we would have had 5 or 6 shades of blue. And then when there's only like 2 shades of blue available, well, each one of those 6 shades has to go with either, A or B. And as you reduce the number of colors, more and more pixels are forced into being something they don't want to be. Okay? So, if the image has so few colors that the number of colors is smaller than the size of the palette, then every pixel in the image will get its own slot in the palette. But if the number of colors is small, then you get this banding. And that's unsatisfactory. So dithering is a technique we use to alleviate that problem. Okay, and here, this image also only has 8 colors in it. So this is 8 colors in it, and this is 8 colors in it. But the dithered one is more satisfactory. It looks better if you sit far enough back from it. Okay? And so dithering is a technique we use when the palette is limited. And what we do with dithering is we simulate the appearance of a color that's not in the palette by arranging colors from the palette together in such a way that, from a distance at least, they have the appearance of the missing color. Okay? So I remembered today to wear my dithered tie, and then I forgot I was coming straight from the gym. So here's the tie I put on this morning, and if I was to ask you what color blue is this here, you might say this is some kind of dark blue. But if you look closer, you'll see that it's not in fact dark blue. It's way dark blue with little bits of grey. But from a distance, now, I'm not sure how far you'd have to go back. Can you see the actual things from there? Does it look like one colour? Or you see the actual pattern? Looks like one colour. Okay, and you're only like 2 meters away. So obviously from way back then, it just looks like one colour. When in actual fact, it's not one colour, it's two colours, in this case in a chessboard pattern. But the patterns can vary. And so, let's say I needed this colour, the one that you see, but I didn't have it. Well, I'm simulating it by using the dark blue and the grey, so that from a distance, I appear to have the colour that I wanted, even though it's not actually in my palette. So here we have the desired colour on the left and the dithered colour on the right, and depending on where you're sitting, you know, they look the same. I actually think they look slightly off, but anyway. If you zoom in, you can see there that in actual fact, it's not the original colour, it's a combination of a darker colour and a lighter colour in the right proportions. It's not great on your screens, it's not great on mine either. When you zoom in, it's like the tie. I think the tie is a better example. Okay, so imagine then you have a light blue and a dark blue in a chessboard pattern. Well then, the simulated colour is going to be the average colour between the two of them. I mean, like if I have, if you imagine, say, a mosaic of tiles, and I put them in a chessboard pattern where I have like white and black and white and black and white and black and white and black, and I lay that out across the library. When the Google plane flies over, it'll probably just see a patch that's 50% grey. It won't see that it's actually white pixel, like, you know, white tile, black tile, white tile, black tile, white tile, black tile. So it's easier to conceptualize when it's a grayscale. I mean, if I had 3 black tiles and 1 white tile, we could see there would be like 75% black. With color, it's a bit more complicated. But obviously, the average redness of the pixels can be calculated by looking at the redness of the pixel, you know, pixel A, the redness of pixel B. If they're in a 50-50 ratio, then the math is easier. And so the redness of the simulated color is the average redness of the colors making it up. The blueness, the greenness of the simulated color is the average of the greenness of the pixels making it up. And similarly with the blue. So you just look at the red and the green and the blue, and you figure out what the simulated color would be. So if we look here, the light blue has a red value of 187, and a green the dark blue has a red value of 51. So the average red value there is 119. The green value of the light blue is 225, and the green value of the dark blue is 51. The blue value of the light blue is 227, and the blue value of the dark blue is 153. So the average there is 190, so that gives us the blue value of the simulated color. So it turns out that 119, 138, 190 is this shade of blue here. My cursor's disappeared. I think it's possible to imagine that if you stood far enough back from this chessboard pattern, it would have the appearance of that shade of blue there. Since it's raining, I'm not going to make someone run outside and have a look. But I wonder if I flicker the screen. No. I could just take off my glasses, of course. No, I'm not back far enough.
Most monitors actually have dithering anyway.
Yeah, it's even more complicated in reality, but we don't want to go there. So in terms of how the image is stored, we organize the pixels this way. So here we have a shade of pink that has a red value of 255, a green value of 118, and a blue value of 205. Here though, the pixels are in a ratio of 3:1. So there's 3 dark pinks for every 1 light pink. So obviously you have to count the dark pink values 3 times. Here I've actually put them in 3 times rather than do a weighted average, because some people ask them to do a weighted average, their brain explodes. So you need to know the RGB values of the color, the pixels, and also you need to know the ratio in which they appear. The pattern may be very ordered. You may be like 1, 2, 3, and 4, 1, 2, 3, and 4, 1, 2, 3, and 4. Or it may look like a pizza with things scattered all over the place. And you may, on a bad day, have to go and count them up just to get an approximation of their ratios. You can experiment and see all this at work in Photoshop. It's actually quite interesting to see how it does it. Okay. Just for this example, I set the red values the same and the blue values the same, just so there was only math to be done. So we count 153 once and we count the 102 3 times. This gives us an average of 114.75, which, as you can see, isn't exactly 118, but it's close enough. And we already concluded that humans suck at color anyway, so it's close enough. So it's really then just a question of working out weighted averages of RGB colors. So here we have pixels of color A, pixels of color B, and pixels of color C. Looking at the ratios there, it seems to me to be a fairly straightforward repeated pattern of AA twice and then B and C once each. Obviously across this whole grid, that's not the case, but you're just seeing a portion of it. If you saw this in an exam now, it would be wrong to count up all the A's and count up all the B's and count up all the C's. You just look for the repeated pattern. And if you take the top left 4 pixels, that pattern is repeated over and over again, isn't it? So, what color is being simulated here then? It's just a question of doing the math. Have I done the math? Oh, indeed I have. I probably got it wrong though. So I'll let you go do it. We could try and do it on our heads, could we? So the 200 for A gets counted twice. So we've got 200 plus 200 plus 200 is 600. C has no red, so 600 divided by 4 is whatever that is. For the green, it's going to be 50 plus 50 plus 10 plus 100, which is 210 divided by 4. And for the blue, it's going to be 20 plus 20 plus 60 plus 50, which is 150 divided by 4. Let's see if my maths is getting better or worse over time. Did I get that right before? Yep, so 600 divided by 4. So the red is 150. The green would be 50, 50 plus 10 plus 100. It's 210 divided by 4. Gives a green value of 53. And the blue would be 150 divided by 4. Is 37 right? Seems a bit low. Yep. Is that right? Did you get the same answer? It's just weighted averages. You just take the red, take the green and the blue completely separately and then work out the weighted averages. I think if you can do these, then you thoroughly understand what's going on with dithering. Okay, here's a harder one. So we're simulating 260-80. And two of the colours we have in the pattern are this and this. What then is the missing colour? That's not so easy. Again, it's just weighted averages, but the weighted average is the answer. So the question is, what's the question? It's fairly clear that the pattern is 2 x's, 1 y, 1 z. We're small but stuck for time, I think, so I'll spoil the surprise. So we've 2 x's. So we've got, well, if we look at the green, look, okay, we've got 2 gx, okay, plus gy plus gz over 4 is going to be equal to, what's the desired colour? Was 60, okay? So that's going to be 50 plus 50 plus 10. So it's going to be 110 plus g divided by 4 equals 60. What's g? You know, there are people in the world that can't do that, can't solve that. If you're one of those, don't attempt a question like this in the exam. But that's trivial, really. Once you figure out that much, the rest is just sorting it out. So it's the green. I worked out the blue to be 220. Did you guys work it out at 220? You could plug in 220, see if it works. 20 plus 60 plus 220. Sorry, 20 plus 20 plus 60 is 100. Plus 220 is 420. 420 divided by 4 is what? Doesn't sound right. Did I get it wrong? You tell me. So I'll put that up in a second. I just want to finish off. So the point is that when you're dithering, there's a color you want and you don't have. And you can simulate having that color by arranging colours you do have in the right proportions. And so the average RGB values of the colours that you have available to you would be close then to the RGB value of the desired colour. So it's just a question then of working out the weightings. And like I said, thankfully we have programs that do this for us, but probably just as well in my case. So we can agree the green is correct. Yeah? The red and the blue would be just the same then, although I don't like to look at that BZ being 220. I'm not convinced myself.